Καλησπέρα σε όλους. Ευχαριστώ για την πρόσκληση, ευχαριστώ που είστε εδώ. So I'm switching to English now since this is the norm that we follow. So let me just introduce myself first. My name is Athanasios Voulodimos. I'm an assistant professor at the School of Electrical and Computer Engineering at the National Technical University of Athens. I'm a member of the Artificial Intelligence and Learning Systems laboratory of the school.
Can't hear you.
You can? Okay. Is it better now? Yep. Okay. So, let me just begin by underscoring the fact that having a session on generative AI and which actually reflects the power and of this term that this term has gained over the last few years is a very interesting fact. As a matter of fact, we all know, we all hear how much generative AI has been coined as a buzzword, right? Or Gen AI or stuff like that. It's interesting because up to just a few years ago, if you think about it, generative modeling, the part that generative models in general in machine learning used to be such a small part in in machine learning, in what was considered as a typical machine learning curriculum. So generative models, I mean, barely made it through in a machine learning curriculum just a few years ago. Just some references to the Boltzmann machines or deep belief networks or such. It's interesting how in just a few years there's been such a rapid, such a revolutionary progress that now generative AI is considered to be one of the most disruptive elements of the whole AI and deep learning revolution. So I'm happy to have the opportunity to just say do a brief introduction into the basic elements and ideas of generative AI in this talk. So we'll go through the outline of the talk will be actually to just get a glimpse of the basic models, of the basic ideas of generative modeling, up to what, and to just touch on what right now is the underpinning of this revolutionary progress that we're witnessing across different domains, especially in the image and vision domain, but not only. So I should start just referring to the distinction, just talking about the term generative AI, and because it's very often used, I'm not sure that it's that everyone is fully aware of the origin, right, of the provenance of the term. So generative AI stems from generative modeling, generative models, as opposed to discriminative models. Most of you probably know that discriminative models are the types of machine learning models that are able to discriminate between different kinds of data instances. Whereas generative models try to produce new samples of data. If we put it in a probabilistic perspective, discriminative models try to capture the conditional probability P of y, where y is a family of labels given x, where x is the input data, whereas the generative models try to learn the joint probability or just the probability P of x if we don't have any labels in our disposal. So I'm going to start to just pass through to first mention, just talk a bit about variational autoencoders, the first important member of this family of models. But to do that, I will need first to make a brief reference to what to some theoretical elements on which they're based. So I'm going to briefly refer to autoencoders and dimensionality reduction. Dimensionality reduction, as most of you probably know, has to do with reducing the number of elements of elements that describe the features that describe data. So this decrease, this reduction can be done through feature selection in what we just select a subset of some features of the existing features, and we just don't pay any attention to the rest, or through feature extraction, where we somehow craft new features that combine, that better represent the information, that effectively consolidates information. So dimensionality reduction and all this process is a very useful process and essential process in a lot of different scenarios. So one of the most well-known techniques to do that is PCA, principal component analysis, where its goal is to create a set of independent new features that are linear combinations of the old, let's call them, features. So these new features are designed in such a way so that the projections onto the subspace that they create closely resembles to the one of the original data, right? So and the objective here is to minimize the approximation error when we represent data using their projections, their new form, onto this chosen subspace. So, how do autoencoders come into the game? So, autoencoders are models that comprise two different elements, an encoder and a decoder. The encoder generates a new representation based on all features, whereas the decoder does the reverse process that reconstructs the original data from the new representation. So the encoder compresses, in a sense, what it does is a process of compression, right? From the initial space to an in-between, to an interim, to a latent space, as we call it. And then the decoder decompresses this data. Of course, depending on the distribution, the latent space dimension and other factors, this process can be lossy. And of course, some information will not be able to be recovered during decoding. So, the fundamental concept behind autoencoders is that we use a neural network for both the encoding and the decoding process. So we have a process of learning which is achieved through an iterative optimization process, and then the output of the entire process of the encoding and decoding process is then compared to the initial data, and then the error is back propagated through the architecture through techniques that resemble techniques that you know and that have been mentioned and will be mentioned in other talks of this summer school. So how content generation and how generative modeling, how new sample generation comes into place in the autoencoder concept. So here, we talked about this latent space. If we assume that if this latent space is well structured, well organized, random points from this latent space that we've learned through the encoding process can be used can be decoded to generate synthetic content, right? From the synthetic content in the context of the data set that we're training at, okay? Of course, it's quite challenging to have a guarantee beforehand that the encoder will be able to organize the latent space in such a way as to guarantee a desirable outcome in the generative process. So often the high degree of freedom that of the autoencoder results in overfitting, which means that some of the points in the latent space are just meaningless, are just useless when decoded. So to be able to use this concept for generative purposes, we need to ensure that this latent space is regular. The variational autoencoders are a version of autoencoders that exactly have properties, regularization properties that prevent overfitting and try to ensure that the necessary properties are in place for generative process, right? And we'll see which properties these are. What's important to note is that to introduce this regularization in the latent space, the process undergoes a modification in comparison to the simple autoencoder case. So instead of encoding an input as a simple data point in the latent space, this is encoded as a distribution across the latent space. Okay. So to achieve the desired regularity in the latent space, as we said, we need to define and to be able to make sure that two properties are fulfilled. One is continuity. Continuity has to do with the fact that two points that are closely related in the latent space should be also relatively closely related to the output to the decoded space as well. So we should not have for example, we should not have, as in this case, two data points that are quite close to each other in the latent space and that are then not closely related in the decoded space, okay? And the second one is completeness, which implies that for a chosen distribution, a point should yield meaningful content and not useless, meaningless content as in this case. So of course, as previous speakers have said already, I'm just missing out. I'm just omitting a lot of the complexity because we neither have the time and nor is this the goal of this of the talk and of the summer school. So variational autoencoders though were just the first model to give quite impressive results in terms of generative modeling. Here's an example of some faces being produced through variational autoencoders. You can see that others are more realistic than other ones. A few years ago, this would have been considered quite impressive. With today's standards, as we know, with the tools that we've seen and the progress that we've seen, this is far from satisfactory, of course. Okay. So, moving on, the next stop in this itinerary on generative models, on the important parts of the generative models, is generative adversarial networks, GANs. So, I'm sure you've heard of them. GANs actually for a period of 3 or 4 years were considered to be one of the most, or maybe the most exciting idea. Also Jan Lacan had explicitly said that back then that he thought that GANs are the most interesting thing and the most exciting thing that has happened to machine learning for quite some time. And in fact, at the moment, at the time, how shall I say it, intelligent and beautiful idea, with, of course, however, some problems then in the implementation, and that we're going to mention as well. So what are GANs? GANs are networks, are actually pairs of networks that include, a GAN includes a generator and a discriminator. These are two networks that are trained adversarially, hence the name. So the generator learns to produce the target output, whatever this is, depending on the data set that we're interested in and that we're working on. And the discriminator learns to discriminate, to distinguish true samples from fake samples. So the generator tries to generate plausible, realistic data, while the discriminator tries to pinpoint which data are in effect real, and which are, on the other hand, are fake and produced by the generator. So the idea is that through this process, the generator is driven to become increasingly better at producing realistic content, whereas the discriminator is also becoming better at distinguishing real from fake, right? In the beginning, of course, how does this work? In the beginning, the generator, of course, creates non-realistic data, obviously fake data. For example, let's say that our application here, our scenario, has to do with producing images of bills, right? Of dollar bills. So, okay, here's the first attempt. It's quite obviously, blatantly fake, okay? So the discriminator immediately discards it as a fake one. As the training process continues, the generator then becomes better in locating the characteristics of what a realistic dollar bill looks like. So if the training goes well, if the training of the generator goes well, then the discriminator will at some point start getting worse at telling the difference, and at some point may be fooled and not be able to classify fake data as indeed fake, and may be fooled to classify it as real data, right? And then its accuracy will decrease. Let us just glimpse through the basic architecture. Mind you, of course, what I'm presenting here is just the I'm sorry, the vanilla architecture of a GAN, right? There have been many different versions and many different extensions of GANs. So, as we can see, the output of the generator is directly connected to the discriminator input. So the discriminator here receives as input samples from the real data set, right? Real samples of dollar bills, for example, real images. And it also receives the output of the generator, what the generator creates as output. So the discriminator tries, based on its loss, to classify, to make the classification as correctly as possible, trying to distinguish the real data from the fake. Of course, there can be different network architectures appropriate to the data each time. It's important to note that during the time that the discriminator trains, the generator does not train. It remains constant. So its weights remain identical while it produces example for the discriminator to train on. Okay? And vice versa, as we'll see at the next. So the discriminator has to connect to two loss functions. The one loss function during the discriminator training, it ignores the generator loss and only has to do only uses the discriminator laws. And during this process, it penalizes the discriminator. The discriminator loss does what? It penalizes the discriminator for failing to identify fake data, right? So based on this penalty, the discriminator updates its weight through backpropagation through this discriminator loss. On the other hand, the part that trains the generator, it includes the random input, which could be random noise as a beginning. Again, on different versions of GANs, on conditional GANs, for example, there can be modifications here as far as the input is concerned. Then, what else is included in the generator training? Of course, the generator network itself, which transforms the random input into a data instance sample. The discriminator network, which classifies the data that has been produced by the generator, its output, and the generator loss, which penalizes quite the opposite in contrast to the discriminator loss. So the generator loss penalizes the generator for failing to fool the discriminator, right? So we did stress that we do not want the discriminator to change during the generator training. When the one network is training, the other one remains constant, and vice versa. So as you understand, this is a different type of neural network. It has some novel characteristics in the sense that we're talking essentially about two networks that are trained adversarially. And this is actually quite the core of the difficulty of the challenge in effectively training GANs. There are different challenges and complications that have to be addressed when it comes to GAN training. There's two different kinds of training that need to be juggled at the same time. And the convergence of GANs is hard to identify. So the process is that, okay, the discriminator trains for one or more epochs, then the generator trains for one or more epochs, and we keep the generator constant during the discriminator training. So as the discriminator tries to find out how to distinguish real data from fake, it tries to learn how to recognize the generator's flaws. Of course, this becomes better. Actually, it's more difficult to do when you have a thoroughly trained generator that produces more informed samples rather than in the beginning. So it's actually this back and forth, this back and forth through the different training processes that allows GANs to tackle generative problems that are otherwise intractable. I mentioned that there are problems often with convergence and problems with the stability of GANs. So one of the most important problems in GANs is called mode collapse. Mode collapse is probably one of the most important limitations of GANs, and it actually has to do with the fact that when the discriminator finds a way to produce samples that effectively fool, when the generator finds the way to effectively produce samples that fool the discriminator, and they consistently do that, it's highly likely that the generator will be trapped, in a sense, will be limited to producing very similar samples, since these samples effectively fulfill their goal. Actually, since it attains the goal of fooling of confusing the discriminator. On the other hand, this is not satisfactory for us because what we want is not just for the discriminator to be fooled. We use this tool just as a process to generate realistic samples. And we need and we want to have, excuse me, we need and we want to have sufficiently representative and rich and a wide range of different samples. We want to generate content. We don't want to be generating content that is very similar, that the produced samples are very similar between one another, right? So this is one of the main problems facing GANs, and the GAN convergence problem is a very was and is a well-known and difficult issue. It's one of the reasons that actually GANs did not, in the end, take off in the way that we expected at some point. I mean, GANs were, in fact, the state of the art for some years, and they produced amazing results. But then, on the one hand, the difficulties that I mentioned and other limitations as well, and on the other hand, the advent of the next best thing, which did take the place of the state of the art eventually, is the one that dethroned them from the first spot in generative modeling. And just an example of some faces again. If you compare with the previous one, I think you'll be. It's safe to say that it's much more realistic. Mind you, all these faces are of people that do not exist. All these faces are synthetic, right? They're not photos of real people. They're images that have been generated synthetically by a GAN. Okay. In fact, I should have included it actually. There's a web page. It was quite amusing at the time, but it's still on if you'd like to check it. I think the URL goes thispersondoesnotexist.com. So if you just click on that, every time you click on that page, it produces a face. It gives you an image of a face of a person that does not exist. And right at the bottom right corner, it also gives you the exact version of the GAN that was used to produce this, right? And also a link to the paper, I think, right? It's interesting you could just look it up yourselves and have a look. So, okay. We said that, GANs were quite amazing up until they weren't anymore. So what's the next thing? Well, the next thing is diffusion models. Diffusion models are what is today the state of the art and what is behind today's greatest, most impressive strides in generative modeling in terms of image and video. Behind Stable Diffusion, tools like Stable Diffusion, if you've heard of it. So diffusion models are inspired by non-equilibrium thermodynamics, and what they do is that they gradually perturb data with noise. They follow an iterative forward diffusion process, and then the goal is to learn a reverse denoising process, a process that removes the addition of noise, in which process then the model becomes able to generate realistic samples. So what the goal is here is to produce a probability distribution actually for a specific data set. Okay, let's say for a data set of human faces, of flowers, of whatever this is, or more complex things or scenes, and then have this distribution to sample it and produce new elements. Diffusion models learn the latent structure of this data set by modeling the way in which data, the different data diffuse through their latent space. So in the forward diffusion process, noise is gradually added to clean data until they are broken, the structure is broken, and then the backward the reverse diffusion process is the one through which we use to generate samples. Okay, because of time, I'm going to skip some technicalities. Again, diffusion models were first proposed, I think, around 2017, however, or 2018. However, they're diffusion models, I mean, for generative modeling. However, it's been the last 3 or 4 years that there's this huge buzz with their use in generative modeling. It's important to note that, first of all, that the abundance of compute and of infrastructure is a determining factor, because they do need to train diffusion models. It's a quite computationally expensive process, so it's not a simple one. So this has GPUs have of course made this easier. And the other thing is that aside from the vanilla diffusion models, of course there have been proposed extended versions and enhanced versions that improve the process, the generative process or the sampling process, or make it less demanding in terms of training or of computational resources. For example, one of these examples is the score-based models, where we actually model the score of the probability density as the gradient of the log of this probability, because we're focusing our interest not exactly on the absolute probability of a certain sample or of a certain image, but rather than on how likely a certain image is compared to its neighbors. For example, how much more likely is an image of a dog or of a cat having 2 whiskers instead of 3, for example, or stuff like that. So I mean, there's of course, as in every part of in every subdomain of AI and machine learning these days, there's a huge amount of research work being produced right now. The top conferences in machine learning, in ICML, in NeurIPS, ICLR, but also in computer vision, CVPR, SCCV, the last 3 or 4 years, there are many papers proposing new versions of diffusion models and tackling problems of diffusion models and improving them to provide better generative results. Okay, moving on. Yeah, some examples. Right, these examples are just straight off from tools that you've probably heard. DALL-E 2, for example. In the middle, you can see the prompt, the textual prompt on the caption: cherry blossom near a lake, snowing. You can see what DALL-E 2 produces, what Stable Diffusion produces, and also, yeah, you can see the second line: eerie forest, black and white at night. Okay, mind you, again, these are kind of obsolete already. I mean, new impressive tools and improved tools are released, every other week or so. Yeah, or you can see the dark alley at night, 4K raining aesthetic. I mean, it's impressive, I think, right? Actually, the projector at some point doesn't do full justice to the quality of the content, of the generated content, I think. If you see the presentation itself, or if you see directly the images on your laptop, they're even more realistic and impressive. So we mentioned, actually, just wrapping it up before going in to see some applications on which I'd like to browse through before the end. We mentioned three different families of generative models. We started with variational autoencoders, whose one of their main limitations is the low quality of the samples they create. We then mentioned GANs, which were impressive and produced better quality images, but had problems that had to do with the stability of the training and the problem of mode collapse. And the diffusion models being the state of the art right now, but from their own side, they have their own problems, requiring many thousands of neural network evaluations. They're quite computationally expensive in real world problems. And they're quite slow in their generation often. Very briefly, as a response to this, consistency models have been recently proposed as an extension, as a improved version, new family of models, creating high quality samples by directly mapping noise to data. And they can map any point at any time step to the trajectory's starting point. So I wouldn't go into details. I mean, you can see if for anyone interested, all the different methods and models are referenced by bibliography, by the papers that you can look into more detail if you want. And this is also true for the applications that I'm going to show you, because unavoidably I will pass through them quite quickly. Moving on, let's just see, after we saw some even quickly some of the theory, let's look at some applications of what these impressive models can do. So one of the problems where diffusion models have been recently used is image super resolution. So image super resolution, I'm sure you're fully aware, means increasing the resolution, producing high resolution versions of an image, right? Of a lower resolution image. So just 2 years ago, there was a cascaded diffusion model proposed, which actually is a pipeline of different diffusion models that can generate images of increasing resolutions on different levels of resolution, right? So you can see, for example, here they're starting with a prompt, a text prompt, Irish setter. We first create a 32 times 32 resolution image of a dog, and then which is then further upscaled to a higher resolution. In painting is another task. In painting is the task of adding content to an image in a specific region of the image specified by a mask. So usually what the idea is in image in painting is that we have an image where a part of the image is missing either completely or is destroyed somehow, or it's occluded somehow. So we just need to, in paint, to fill in this part at some point. So a CVPR paper from 2022 proposed repaint, a diffusion model to tackle the in-painting approach. And let's see some results. Right, you can see the input, okay, for example, of and you can see that it works, this particular model works on very different types of masks. Here it's a mask which covers half of the girl's face. Here is a much less regular mask with different irregular shapes and the pixels missing. Here half of the image is missing. So in all cases, this tool, Repaint, was able to sample multiple diverse outputs and produce an effective result. Quite similarly to in painting, image-to-image translation actually is a family of tasks. Image-to-image translation means translating an image to another one. So this could actually encompass different subtasks. It could be colorization, taking a black and white image and producing a colored version. It could be in painting that we just mentioned. It could be uncropping. So imagine that we have a cropped version of an image and we want to uncrop it to reveal, to fill in the missing parts. Okay. Or it could even be a restoration from a JPEG, from a compressed image, and seeing what the compressed artifacts, removing compressed artifacts and restoring realistic image detail. Other important, very interesting task, style transfer. Style transfer was actually one of the most interesting and exciting tasks that were encountered by GANs. Style transfer means manipulate an image in such a way as to adopt the appearance or the style of a specific type or of another image, maybe. So yeah, here you can see here, for example, we have the Mona Lisa and the Starry Night of Van Gogh, right? And these are mixed somehow. So yeah, this particular work, style injection in diffusion, it's a paper of this year. It was just presented in CVPR 2024 just last week, actually, in the CVPR conference in Seattle. Yeah. And last but not least, I'm just going to quickly refer to some applications of diffusion models in the medical field, and I'm just singling out the medical field here because I think it's quite a significant thing to note that a field like biomedicine, which excuse me, which needs to make sure that we have trustworthy solutions, right? And it's one of the most highly where reliability plays a major role. Generative AI and the power of the generative modeling, being able to contribute there is something very, both at the same time, impressive and important, and to be careful of. So there have been studies, there have been papers which show that the use of synthetic data produced by diffusion models can improve performance when used to train classifiers for histology images. Excuse me. There was an interesting study just last year showing that where the authors conducted a survey showing to experts, to medical experts, to pathologists with different levels of expertise, showing them images, histology images created from diffusion models and real histology images, and it was revealed that quite a significant part of the panel could not distinguish real from synthetic images. Then, again, image-to-image translation that we just mentioned can be crucial in the medical field as well. There have been shown favorable results when talking about cross-modality problems like MRI to CT or filling in missing modalities of data. And the same goes for for other biomedical problems of interest, such as image segmentation, image denoising. I'm just passing through because don't want to miss the time. And anomaly detection is a very interesting case as well, where we just compare the input image, the unhealthy input image, with the generated healthy one to detect the anomaly present in the medical image. Here's just, I know it's not really legible to you, but it's just to give you an idea of the taxonomy of the diffusion models for different applications in the biomedical field, right? So I'm just here's another application, MedFlamingo, a very interesting multimodal medical future learner based on diffusion models and the visual question answering. You can just feel free to have a look at it, or just let me know we can discuss anything related right afterwards. So thank you very much for your attention. If you have any questions.
Thank you, Thanos. Any questions? We have some time for questions. Yes, please.
Hi, thanks for the great presentation.
No.
Just I think a minor technical question. Sorry if it was answered that I didn't notice.
Yeah.
Regarding the diffusion models, what I'm missing is where the prompt comes in. We know the noising and denoising procedure, but where do we input the prompt so that we can guide the image generated there?
The prompt, you mean the textual prompt?
There's
not necessarily a textual prompt. First of all, in the plain case, we just have the images. Yeah.
Exactly, that's what I say. But then we have the examples from stable diffusion, etc., where we have a textual prompt that is transformed in image. In what procedure do we have just a latent space that we just have something aligned on the image part and the text? Is there a different procedure? Because like in the LLMs, the generative procedure is clear because just the same modality.
Yeah.
But here we have a shift of modality. So where is the textual prompt transformed in an image?
I mean, it could be. It depends. It could be though in the it could be tied in the forward process of the step. If I understand your question, but I mean it's. Did you link it to LLM? Sorry, what
No. The LLM was just a parallelization. That it's clear how the input drives the output, how we can guide the output. So the question here is like how we guide the stable diffusion so that it produces an image that we want.
It can be done in the forward diffusion. It depends on the solution. It can be done in the forward process. We can see more in detail stuff offline.
Okay, thank you.
Yeah, welcome.
Usually, you have a latent variable input, something like that. And,
Excuse me?
You have a latent variable input, and then you generate from that.
Yeah.
Any other questions?
I actually had the exact same question, but just to extend it a bit, how does that translate to architecture? Like, how does the input prompt, for example, or any other, like an input image, for example, take part in the architecture and the forward pass, as you mentioned? Like, is it an embedding? Like, how does that all work, especially during the training phase?
How does an image? Sorry, I didn't hear you.
The prompt, the input prompt, like from the language model. How is that trained? And is it trained in the is it all trained in one pass, in one step, in the forward pass, or are there more ways to train it, to associate the input prompt with the sample image during training?
Yeah, it can be in the forward process, but I mean then in the latent space, the joint the embedding in the latent space can be tied. I mean, in the latent space, you tie the prompt with the image. But I mean, depending again, it's quite depending on the different type of solution that we're talking.
Right.
So, yeah. Okay.
Okay. Well, thank you.
You're welcome, Nico.
Hi. I wanted to ask, so you explained about discriminators actually gradually losing the effectiveness on actually detecting something. Yeah. My question was that, okay, well, maybe if you could explain it again why it loses and it's actually getting confused and not being able to actually detect anything at that point. And then also I wanted to ask, what's the best percentage of detection we can actually achieve, and is there a way we can actually maintain that, or are we doomed in a way to actually start gradually losing that detection?
What was the second part of the question?
I meant like if there is a way we can actually maintain that percentage of detection, or are we like doomed in a way that the percentage is going to go down, so we're eventually going to have a discriminator that detects less? That's
no, I mean it's not. Yeah. Okay. Yeah. There are techniques that you can follow to try and avoid or delay or not have it appear at all. But I mean the problem of this, how to put it, of this deterioration actually has to is connected with the fact that I mean what the discriminator when this appears, what the discriminator gives becomes less meaningful over time. So at some point, if the generator has become too good at this point, and this is a case, one of the cases that this could happen was the case that I mentioned before, that it has found a space where it always effectively fools the generator, the discriminator. Then to get out of this space, you have to do techniques in the training. You have to give maybe to follow some augmentation techniques or follow some techniques to try to make it to evade this difficult place. But again, this is the only this is one of the problems. But I mean, this is not actually the only problem. So even if you achieve in a specific application or a specific scenario to alleviate this problem, the issues of stability and convergence still do exist, and this is why in a significant extent GANs have been quite rapidly. I mean, there has been how shall I say it? A fall of interest, a very impressive fall of interest in the use.
Okay. Do I have time to ask more? It's a more of a philosophical question, but it just came to my mind, and I just wanted to
philosophical is nice too.
When you explained that everything goes so fast, and every as you mentioned, every week or something, a new generative AI comes out. Do actually graphic designers face, I would say, an issue, or maybe an enemy? Because at that point, when we reach a point where generative AI is so good, it can generate any image we want. So then a graphic designer, you could say, possibly wouldn't be needed. Just as a philosophical question, but I would like to hear your point.
Okay, you said graphic designers, right? You talked about graphic designers. Actually, this is a discussion. This is a discussion that ranges not only for as far as graphic designers are concerned, but actually content creators everywhere. So there are huge discussions, and there's significant worry about this, about whether generative AI will be replacing the work, the creativity, human creativity in general, right? It's not just graphic design. So, well, it's not an easy answer. I mean, it would be easy and quite, soothing to be able to directly say, no, don't worry, they won't. Because I'm not sure actually that they won't at all. I mean, to some point, it seems like. In fact, yeah, it's the results and the quality of what can be produced using these tools is amazing. So it's not quite easy to say that there's no such prospect or danger. But of course, we should not forget that all this, to be able to be produced, all this is trained on actual content prepared by humans, right? So in this sense, I mean, human creativity will always find a way. Will always find a way. I'm not sure it will always be superior. I mean, you never know. As it was discussed before, you never know. It could be just, yet another shadow. I hope that and believe that there are always other paths ahead.
Thank you so much. Yeah. One last question.
If I may to comment before my question about okay. So, in my opinion, I am a technologist, a laboratory technologist, and I often say to our students that AI will take our jobs because we saw at an earlier presentation, I think, a radiography, and AI was annotating, basically, was making the diagnosis. And I'm saying to them that, I'm joking when I'm saying to them that it will take our jobs, because it won't. It will change our jobs. It will not substitute us, it will change us. We will have to adapt. Generative AI will be a tool for graphic designers to create their own content. This is what I think. It will change how we do things. It is a tool. We will use this tool. I don't know if it's better or worse from, I don't know, a pencil, but yeah, okay. It will be used as such. Now, my question. Yeah, I have a question as well. Did you want to make a comment? I'm sorry. So, as I've said, I am into the field of biomedical, and you mentioned that. There is a project that I want to do with a student, and basically there are many neural networks that do that. They are trying to predict, they take as input images or videos, but let's not delve into the videos now. They take images of cytology, of chitology, and they try to predict what kind of cells there are in this image. Yeah. The problem with that we face is that ethically the patients will need to, basically what we want to do is to take images from real samples and annotate them. We will annotate them, or the doctors will annotate them, and we will test the algorithms with what we will consider correct annotation that was made by the specialist. The problem with that is that the patients may need, probably they will require, to give their consent. And our problem is, what do we do if we do not have that data? So my question is, and I think you said that can we use generative AI to generate such data in order to test another algorithm, another neural network that tries to do that? We will use data that are somehow available, and we will train the generative AI. Is that feasible? Is that feasible? And is it feasible to do that with what hardware?
So, if I understood the question, you mean if you can use
synthetical data.
Excuse me?
Generate synthetical data.
Yeah, generate synthetical data to use for training, right? Because you can have access to real data.
Right.
Yeah. I understand. Yes, I understand. So you generate synthetical data. Yes, in principle you can do that. Under circumstances, you always will need some real data to produce the synthetic data. But yes, in principle, this is what these works are alluding to as well. That you, in principle, can. Yes, that's the answer. Well, the diffusion models do require.
You can discuss that.
Yeah, we can discuss it offline.
Okay.
Yeah.
We are running out of time.
Sure.
So please.
Thank you.